Hi, and welcome to this Microsoft Research webinar. I'm Sai Vemprala, and I'm a researcher with the Autonomous Systems Group at Microsoft. And today, I would like to talk to you about the role of simulation in AI, and specifically our open source robotics simulator offering that we call Microsoft AirSim. Over the course of this webinar, I would like to introduce the features of AirSim, and also go through some sample research projects that I've used and benefit from AirSim's features in the past. And towards the end of this webinar, I'd also like to go through a quick demo of AirSim features so you as a researcher can get started with using it. So a little bit about the Autonomous Systems Group and myself. So I've been a researcher with Microsoft for a little less than a year now. And before that, I got my PhD working on the idea of collaborative drones, typically localization, planning, and more classical robotics things. And at the Autonomous Systems Group, my focus is on what we call colloquially training brains for robots, or these are the decision-making pipelines that drive the robot's actions. So to this end, I examine things like robust neural networks, learning invariant representations for robots, and also the idea of bridging the simulation reality gap using simulators like AirSim. So to begin with, as a primer, I'm going to talk about autonomous robotics in general and what are the challenges that require AirSim as a simulation, right? So as we all know, autonomous systems today have a large array of applications, and some of the most popular ones in them are things like self-driving cars, and for example, drones that are supposed to be doing package deliveries and things like that. So as we can see, many of these applications involve a certain proximity to humans and also, for example, industrial equipment. And one thing we have to note is for robotics specifically, there is the autonomy aspect of it, which can be treated as decision making. And then for every decision the robot makes, there is a corresponding action, which is like the actuation or the movement of the robot. So combining the fact that it's moving and what I just described above, that its proximity to humans and things like that, it is extremely important to focus on things like safety and robustness. So that is not something we can compromise over. So whatever policies that we use, whatever actions the robot takes, have to adhere to certain safety constraints. And at the same time, when we think about real life applications, the real world is hard to model, right? So we have very complex sensing. For example, even something as simple as a visual camera has a very complex input space. And the environments that the robots work are quite diverse, and the actions they take are also quite complicated. So these are some areas where machine learning typically shines, right? So the idea is to build autonomous systems by leveraging these nice concepts for machine learning that let us deal with complex data spaces. And of course, one of the challenges so far is that autonomous systems research is not new. So it's been around for a long time. And a lot of the focus so far has been on classical techniques. So things like computer vision and classical robotic pipelines have been applied. But of course, as we move on to more complex spaces, these are not sufficient. So we'd have to move to more of a machine intelligence perspective using neural networks and deep learning and so on. And of course, when we start talking about deep learning or neural networks in general, there is always a large dependency on data. So these are data-driven methods for a reason. So we would have to come up with some kind of labeled data, for example, for supervised learning. Or if we start talking about reinforcement learning and such, we need to have places where the robot can explore and understand the interactions with the world. So considering the fact that the final test case is going to be in real world, it's really hard to have a scalable method to get real world data for such a large dependence, right? So it's almost impossible to get all the corner cases right by training an agent in the real world. So let's dig a little deeper into what exactly is happening in an autonomous system, right? So an autonomous system is composed of what we call a perception action loop. And if you think about it, this is very similar to what we humans do on a day-to-day basis. So a robot typically perceives the environment around it. This is through the use of sensors, typically. And on the picture on the left, for example, you can see that there is a self-driving car that is trying to look at some of the objects around it, like the other cars, signposts, people, etc. And this perception needs to result in an action. And again, for the self-driving car, this is something like the steering commands or the throttle and brake and so on. But the interesting thing here is that the perception and action are quite tightly coupled in robotics, right? So every perception results in an action, and the action also, again, drives the perception subsequently after that. So what we need to do is we need to learn these loops in a very tightly coupled fashion. It's not enough to just focus on one part of the task and then let the other, happen by itself. So the focus in a data-driven method would be to learn these from both the sensor data as well as the corresponding interactions. So if we look at some of the, the typical classes of learning, and we have, for instance, supervised learning. For supervised learning, we would need labeled data that is kind of task specific. When we start thinking about reinforcement learning, for instance, like I mentioned before, we would need to have a sandbox that gives us the ability to take actions, and then each action would have a reward, which is the typical RL paradigm. And then even if we consider something like imitation learning, which is like a subset of supervised, then we would need, for example, data traces of what actions has an expert taken. And the imitation learning part is about imitating an expert. So we need expert data, and then we would have to take those actions and then train our agents correspondingly. So given these needs and challenges, what is the most effective way to train artificial intelligence for real-world robotics? And the biggest thing that pops up is this dependence on data, right? So here we look towards simulation as a possible way forward. So as we all know, modeling and simulation are one of the cornerstones of engineering. So whenever we talk about any kind of a complex system, for example, in the pictures here, we have some samples. Think of, for example, an aircraft, right? So most of the pilots typically train on simulators before they move to real aircraft. And when we think about complex engineering systems like computational fluid dynamics or climate models or anything that is a sufficiently complex system, one of the first things we do in engineering is try to approximate it the best way possible. And by characterizing it as well as we can, we have the luxury of getting a lot more data without having to deal with the actually complex system. So for things like robotics or any real-world engineering systems, the advantage is that we don't really care about things crashing or breaking because we have the luxury of just restarting the simulation and then learning from these failures as time goes on. So even if we consider just machine learning, we have seen a lot of success in the use of simulation and machine learning concepts. So for example, a lot of you may have seen the success of reinforcement learning in solving many of these video games or complex games like Go and chess, right? So what we call these are like closed world systems that let you simulate millions of trials in a very easy fashion. So these agents can sort of learn from their mistakes and learn the mechanics of the games and then get better and better until they even achieve superhuman performance in some cases. But the catch is that most of these require many, many frames of play, right? For example, some of the initial work on Atari required about 10 million frames to get to a reasonable level of performance. And then very recently, there was something called Agent 57 released by DeepMind, which achieved superhuman performance on all 57 Atari games. And this required, for the max performance, about 80 billion frames of play. And if you think about OpenAI 5, which is the agent that successfully placed Dota 2, this required something equivalent to 45,000 years of Dota self-play. But of course, I mean, this is being done in a very, very fast distributed fashion, so it only spread over about 10 months of real-time training. But the idea is that to get to this level of performance and to get to this level of robustness, it's always important to have a system that you can use to the maximum. So it's something you can explore and exploit and then come up with these strategies and then find which one works the best. So now our question has an answer. So why can't we kind of leverage these high fidelity simulations for robotics? And I want to emphasize the word high fidelity here, because when we start thinking about the real world, it's not like just a video game, right? For example, in the previous slide, we talked about these video games. That game that you're seeing on, for example, on the bottom left, the Pac-Man, that is the system that you want to train on. So the simulation is exactly the same as your test case. But for robotics, we have the real world, which is actually quite hard to approximate. So we want to get as close as possible in our characterization. And we want to build these large-scale, accurate simulations so these machine learning-powered robots can learn in these worlds, and then we should be able to transfer what we learn in terms of policies into real-world operations. And to this end, we present what is called Microsoft AirSim. And AirSim is a tool that tries to address the high fidelity requirement in two different ways. So the first one is visual fidelity, and you can see from these pictures on the left and the right that AirSim has a very good graphics engine. So this is because it links up to AAA video game simulators or video game engines. We typically mainly support Unreal Engine, but we also have experimental support for Unity. So you can see that the worlds are quite realistic as compared to real world. And then we have access to many features such as realistic lighting, high resolution textures, and so on. And the advantage of all of that is that our vision or perception pipelines are now learning in something that is trying to replicate real life as much as possible in terms of visuals. And the second aspect of the fidelity is the physical simulation of the robots. So we have these robot dynamic models in AirSim that try to approximate the dynamics of the real robots as much as possible. And to this end, we actually have support for 2 different platforms in AirSim. And as you can see here, we have a car and we have a quadcopter drone. So you're allowed to kind of train policies for either of those vehicles while leveraging the visuals and the physical simulation of the robots. So before we go into more detail about AirSim, let's kind of take a broad look at what an AI-centric simulation would look like, right? So let's start from the right, where we have the robot and sensor suite. So first thing we need is, as I've said before, is a physics model for the robot, which is trying to match the real-world physics model as much as possible, right? So, and then, because the robots typically sense or perceive the world through like a fleet of sensors, we need multiple sensor modalities. And to this end, AirSim tries to provide, for example, cameras, like RGB cameras or stereo cameras, LiDARs, IMUs, and so on and so forth. And now that we have all of these sensor or robotic data, we should be able to record them and then have them as training data for our pipelines in machine learning. So we should be able to record these robot states, sensor data, and the corresponding actions as we explore the world. And while all of this is on one side of the coin, the other side is basically the environmental part of it. So this is where the high fidelity graphics comes into picture. So we should be able to interact with a world that looks realistic and feels realistic. So we should have control over the environment. So for example, we want to see moving pedestrians, for instance, or whatever obstructions or distractions that the real world might have that the robot can get confused by. So we can simulate them and try to learn from them. And then finally, and I want to point this out specifically, there is a feature called domain randomization, which is very typically used in AI pipelines. This is essentially saying that whatever my task is, I want to learn this task in many different settings. For example, if I want to detect a pedestrian using machine learning, I should be able to detect the pedestrian no matter what the background is, right? So when I'm training my pipelines, I want to randomize the backgrounds and the lighting conditions and the weather conditions and so on and so forth. So this is the randomization that AirSim lets you do. So at the end of the day, all of this comes together to enable real-world AI with simulation. So to this end, we provide the ability to get labeled data for supervised learning tasks. For example, you can do object detection and segmentation. And you can also do robot-specific things like localization and path planning and so on. And of course, because it's a simulation, it lets you also interact with it many, many, many times through reinforcement learning. So you can have rewards and actions basically driving each other. And then you can have an agent that learns from a realistic simulation. So just a quick or a deeper look into the ecosystem of AirSim. So AirSim acts as a plugin, which is on the right, to a game engine. And then currently we support Unreal Engine and Unity as our target platforms. So the game engine is responsible for sort of hosting the simulation and the world. It contains a lot of objects. It's basically a scenery that you can design by yourself, or you can get started with some of the sample worlds that we have available. The game engine has its own native physics, which is what most of the world operates upon. But AirSim on the right has its own custom physics that it uses for the robots themselves. So this is a little bit more accurate and more easier to work with for the end user. So we can have full control on the dynamics and things like that for the robot. So we have the robot platforms, which is either a car or a drone. We have the ability to acquire data from sensors. And then we also let the users send, control or planning commands basically through a Python API, which is easy to start with. And on the top left, I have a mention of hardware in the loop or software in the loop, which is HITL or SITL. So this is a concept that is very useful for quadrotors, and some of the drone focusing people might know this. So there is off-the-shelf hardware such as the PixHawk or things like that for drones, which typically go on the drone platforms in real life. So AirSim lets us actually plug them in as a hardware-in-the-loop simulation or simulate them internally so we can have comparable performance with the real drone. So whatever we build in the simulation should be able to transfer to like a real drone platform. So in terms of the features and the API the user can use and control, so let's go right to left. So we have the environment where the robot lives. So in the environment, we have access to a lot of different features. So for instance, we can change the weather effects. So we're already having a certain level of randomization here. So we can have rain, fog, dust, and snow, and so on and so forth. We can change the time of day and things like that. So we'll have different lighting conditions. There is ability to control the existing objects in the environment and all the information regarding them, like the poses or the sizes, etc. And of course, one of our failure metrics is typically collisions, right? So when we have a self-driving car, when it collides with something, that's a failure. So we have the ability to continuously record these collisions. And then whenever, for example, a collision happens, you can basically say, okay, that's the end of that episode. Let me train again. So we have that information coming from AirSim as well. And for the vehicle, we have the quadcopter and the car platforms, and we can use multi-agents of those as well. So we can have a swarm of drones or multiple cars in the scene. In terms of controlling the robots, we have something called, like low level, medium level, and high level control. So for the low level control, we can control motors, motor speeds, angular velocities, and so on. And for the medium and the high level, we can do velocity control, position control, trajectory control, and it's up to the task, and it's up to the user to pick which one is the best fit. And in terms of sensors, we have a wide range of sensors that can be simulated. So we have cameras, typically. So we have the RGB, this is the visual camera. We have depth cameras, which give us the per pixel distances to the objects that we are observing. We have a segmentation view. I'll go through some more details later. And then we also have the stereo depth coming in from the cameras. So these cameras can also be controlled. We can control the poses, the field of view, the distortion, things like that. And at the same time, we also have the conventional GPS IMU sensors as well as the LiDARs. So basically, the broad idea is that we should be able to play with any kind of sensor or vehicle parameters that we want. And then we want to learn from these multimodal, rich kind of sensor data. And then we want to train robust and efficient pipelines. So this is a quick overview of what AirSim tries to do and all the access that we have to the features. So let me talk about some sample research projects that we have done over the past, and then how exactly have these projects benefited from AirSim. And over the course of this, I'm mostly focusing on projects that have involved drones. But of course, the same thing can be extended to the cars or any other platform that you would wish to simulate later. Okay. So let's start with a simple perception problem. So this is something that I worked on during my PhD years, and I've made heavy use of AirSim in this work. So the idea is to detect and localize a drone from another drone that has a depth camera on board. And the depth camera is essentially a camera that gives you not only pixel data, but on the right, you can see that it has a certain looking representation where every pixel represents a certain distance. So the brighter the pixel, the closer it is, basically. So detecting drones through a depth camera is very useful because now we can also localize them with a certain distance, and we can write, for example, obstacle avoidance pipelines. So of course, this is not an easy problem because drones can be of different types. The environments can be of different types. There's different kinds of lighting, et cetera, et cetera. So how can we leverage a simulation like AirSim, for instance, to help us with this task? So what we did was we tried to come up with some sample scenes in AirSim. And for example, on the bottom, on the left and the right here, we can see that we've generated some different kinds of environments. So we have indoor spaces, we have outdoor spaces with random objects sitting in the environment, and all of this can be designed by the user, right? So, and in here, what we did was we spawned different drone types in AirSim. So the idea was for each of these drones or environment types, we would generate training data that contains depth maps, which we will, this is the one on the middle, that we will use for the final final testing. And for each depth map, there is a corresponding segmentation map. And then AirSim provides both of those, right? So this acts as a ground truth, for instance. So we can label all of these drones according to their actual locations in the segmentation map. And then we can randomize this for different drone types, different positions, rotations, lighting, and all of these can be changed by the user. And we also try to inject some noise in these images, so the images look, kind of similar to what you would see in a real-life stereo camera. And then one thing I would specifically like to point out here is that in this application, we knew that our target drone had a certain stereo camera. So in our case, it was a Stereolab Z stereo camera. So what we were able to do in AirSim was actually replicate the exact parameters that are used in that camera. So the same baseline and the same field of view were used in AirSim to get as close as possible to the target platform. So we have access to all such features to train a pipeline that's as robust as possible. So once we have this training data, so we were able to train an off-the-shelf detection model. In this case, it was a YOLO detection model. And then we were able to straightforwardly transfer this from simulation to real life. And the randomization is the one that helps the most. And here you can see a video of the target drone, that is the one that's flying here. And then there is the host drone on the left, which is trying to capture the video and detect. So as you can see, when I pause the video, you can see a bounding box that's being drawn around the target drone. So it's able to detect and localize it as it goes through flight. And here we also notice that the perception model that was trained in simulation was able to scale up to multiple drones in real life and also different drone types that it has not seen. So the fact that we randomized it to some extent was helpful in the generalization capacity. So now you can see there are multiple drones flying in the workspace, and the host drone is able to detect both of them, as you can see on the bottom left. So in this last test, we have about 3 drones actually, so it's supposed to detect all 3 of them. And if I pause here, you can see that, there's a drone here, there's a drone here. And so the idea is that getting training data from simulation is actually much more helpful than just trying to get data in real life, because gathering this kind of data in real life would be quite painful. And in simulation, we have the luxury of changing so many parameters that would be very hard to do in real life. So this helps us create a kind of like a robust generalizable model. So this is a classic perception sort of a problem that was solved through the use of deep learning. So now let's look at the action part of it. So what if I wanted to take actions and I wanted to train this a drone in simulation? So this was work that was done by researchers over at Carnegie Mellon University. And then the idea driving this work is actually quite fun. So the question is, can a drone act as an aerial cinematographer? So if I have a test subject, as you can see on the top here, so there's a test subject that is walking in a scene, and the drone is the one that's flying around and taking pictures. Can I come up with a pipeline that lets the drone do this in a smarter fashion? So can it understand what does a good shot mean? Like, what does an artistic shot look like? Right? So what they tried to do was they tried to use model-free methods, and specifically reinforcement learning, to learn policies that will move the drone in a certain way that the shots look good. And for this, because you could have like variety of test subjects and variety of environments and all those things. So again, they tried to leverage AirSim as a possible tool for simulation. So they designed many different kinds of environments in AirSim, as you can see from left to right. So it starts with a very simple environment with just a few blocks, a slightly more complex environment with some obstacles, and then on the right you have a realistic looking scene with a test subject and all 3 of them just walking around. So what they did here was they were able to quickly prototype many kinds of rewards for reinforcement learning. And some of these were human, like handcrafted rewards. Some of these rewards were based on just exploration. Some of these rewards were based on feedback from other people, things like that. So the fact that all of this was spun up in simulation makes it really easy to run through many different kinds of approaches and then pick the best working one. And the fact that they have different environments also makes your policy robust to changes or just animation changes or just changes in the environment and obstacles and things like that. So here's a quick example of how that looks like. So you can see that they were able to simulate movement of, for example, a person in a realistic looking scene, and they were able to go through various kinds of trajectories that are part of the aural training. So this lets us prototype many different test cases and kind of find this policy that's robust enough. So the fact that all of this was high fidelity enough was enough to allow them to kind of deploy this in a real life drone. So they were able to train an agent in simulation and then put it in a real life pipeline. So as you can see from this picture, the drone becomes the director, as the video says, and it has learned only in simulation, but it learns, tries to capture what does an aesthetic shot look like, and then tries to do the same thing. So here you can see it's able to adapt to certain obstacles in the environment, moves to desirable locations, not hit the trees and so on. Yep. So essentially what's happening here is the decision-making aspect of it, or like what action should I take, is being dealt with by a data-driven reinforcement learning pipeline. But I have to note here that most of the rest of the things like tracking the person or planning, etc., are being done in a classical fashion. So the reinforcement learning is mainly for the decision making, for the shot selection. But now it raises an interesting question. So can I do everything in a data-driven fashion? Can I do perception and action, like I mentioned in the beginning of this talk? Can I bring them both together using data-driven methods, and how does the simulation work for that? So here, let's talk about a more interesting question. So on the left, I'm showing you a simulation scene where a drone is trying to fly through a bunch of square gates. Right? If I wanted to learn a policy in simulation, looking at this environment, and then put it in real life, as shown in the right, what would I have to do, right? So what is a representation that lets me go from simulation to reality in the most efficient way? And this is work that's been done internally at Microsoft. And the paper and the code are actually available open sourced. So I'll point you to some links at the end of this talk. So now the question is, I need to do both perception and action learning from a simulation. So here we can break this down into two parts, right? So for example, if the task is to look at this image, the one shown on the left, that is a red gate over there, and I want to go through that gate, which is the task, right? So the first part would be to extract the position or the pose of the gate. So I need to know, where to go. And then I would have to compute the control action that will actually take me there. And the first part, which is the pose extraction, needs to be robust to changes, because even if there is a different background, for example, in the previous slide, we saw that those two scenes are completely different, right? So there's different textures, different everything, except for the fact that there is a red gate. So whatever perception pipeline that I learn has to be robust to such things. And then the control action that's being computed once I know the pose needs to be optimal and fast enough, because it's a drone and we want to do it in a smooth, fast fashion. So this work proposes using what's called a cross-modal variational autoencoder. A variational autoencoder is a generative model which basically tries to learn a compressed representation of any given image, right? So in this task, what this work tries to do is it tries to enforce the constraint that the gate is the only important part of my image, right? So I don't really care what the background looks like as long as I can infer the position of the gate from a given image. So what's happening here is that they're leveraging AirSim to generate a lot of training data for these gates. So as you can see, for example, in the graphic here in the middle, so a drone is being made to fly through a bunch of gates, and then all of those images are being recorded, and then they train a cross-modal variational autoencoder to compress this image. So what's happening here is that it tries to learn a condensed representation along with learning the pose of the gate. So now it knows what, for example, a given picture corresponds to in terms of the pose, right? Okay, so now that I know the pose, how do I learn actions, right? And of course, we can always do reinforcement learning, which is just exploding randomly, but it's not very sample efficient if you think about it, because the robot's going to need to go through many, many, many trials just to understand that going forward is the right action, for instance. So to make things a little bit more efficient, the authors propose the use of what's called imitation learning. So here, again, we leverage AirSim to provide us with what we call expert actions. So we can have a controller inbuilt to AirSim that is made to fly through all of these gates continuously, right? So for every image that we capture of this gate, we can also have an associated control action that's being done by the expert. So now we train a behavior cloning or any imitation learning pipeline to learn from these actions. So now we have very extensive training data, right? So we are capturing data for the perception as well as the action, and then we train this in like a two-phase fashion. So just to recap, what did AirSim do here? So AirSim was providing training data of the images of the drone gates, which is trivial, and then the poses of all the drone gates, because in a simulation, you know exactly where every object is, right? So if you're looking at an object, you know where the pose really is. And then also the expert trajectories from a high-level controller that is inbuilt to AirSim. So AirSim is able to provide all the data for the agent to learn from. So in the paper, and for more details, you can look at the paper itself, they use the variation autoencoder coupled with the behavior cloning pipeline for the agent to learn. So on the right, you can actually see graphics of it working in real life when it was entirely trained only in simulation. So no real life data was used. And the fact that it is it's a variation autoencoder that tries to compress the image. So on the bottom here, you can see that all of these images that are being seen are actually being converted to a representation that was learned in simulation. So you can kind of compare the previous, the grassy environment in AirSim that's still visible here. So all the real images are being understood by the agent in a simulation point of view, and it's still able to take the right actions. So even on the top, you can see it's a very challenging environment with snow and reflections on the ground, and yet the drone is able to use the model trained in simulation and transfer it to real life. So the recap of these projects is basically to say that AirSim has been quite effective in helping some research projects, and there is a more extensive list of projects on our website. So you can go through that and then get ideas on how you can use AirSim as well. But this project, typically, I'm going to emphasize this one a little bit more, because the problem we are facing here, the idea of drones going through these gates, is actually a very interesting research problem today. So we can think of it as a new research direction, essentially. And this is something interesting because it's being driven by a concept that came out of hobby drone racers. So drone racing is actually, as you can see in the video here, it's a pretty popular sport today. So there is something called the Drone Racing League, which hosts competitions internationally with with huge amounts of prize money and so on, very famous and very popular. And looking at these people flying the drones, the research community obviously had the question, like, can we actually have a drone do these insanely complex maneuvers, right? What does it take to have an autonomous drone fly through these gates and in a in like a very fast or very aggressive kind of a flight? So the new research direction now is, can we have autonomous drone racing, and what does an agent that is trying to do autonomous drone racing look like, and what kind of capabilities do we need to train something like that? So the specific reason why autonomous drone racing is really interesting is it brings together perception, planning, and control. So the perception is obviously quite complex, because now we're focusing on such a small, sparse part of the environment. All we care about is the locations of the gates and that we have to go through them. And the planning and control are also very complicated, because now we're supposed to move at very high speeds and do task-specific sensing, just focusing on the gates, for example, and all these maneuvers. And the other thing is the game theoretic aspect, because here you're supposed to win a race. It's not enough to just fly through the gates, but you have to do it as fast as possible. So here we are combining safe and robust autonomy with sort of like aggressive actions and game theoretic planning. So over the last couple of years, there have been many competitions actually focusing on this particular research problem. And one of them was Microsoft's own Game of Drones competition that we co-hosted from our group at NeurIPS 2019. So at the same time, there was a pretty popular competition called the Lockheed Martin Alpha Pilot, which also wanted the competitors to build an autonomous racing drone. And then there is a regular yearly contest that happens at the Intelligent Robots and Systems Conference, which is focused on drone racing as well. And looking at this newfound interest in drone racing, our group has come up with an enhancement for AirSim that is focused on drone racing. So we call this the AirSim Drone Racing Lab. So essentially what's happening here is that we take AirSim and then we give it some extra capabilities that are focused towards drone racing. So now we have trajectory planners that let you actually go through waypoints in space. And this was actually what was used in the work with the VAE. And then we have controllers that can do smooth, fast actions given trajectories. The users can actually generate or use existing racetracks with a bunch of gates. And we also have a lot of racing logic, right? So for example, you can have lap times, you can have disqualification metrics. For example, if you hit a gate or if you hit a drone, you get disqualified. You can log your progress, you can record all the states and actions. So now it lets you actually train these pipelines that are focused on fast, aggressive autonomy that is useful for drone racing. And just another quick addition to that is that we are also, this is an active development, so we're also going to add more features in the near future. So what we are planning to add are things like, mapping pipelines, for instance. So we would have an estimate of occupancy in the maps. For example, if you're going through gates, you need to know that the gate is an obstacle and that should be avoided, right? So we need like an occupancy map, for instance. There is also more robotic specific tools like sign distance fields, which allow you to do efficient mapping and avoidance. The domain randomization factors in again, because we want to be able to train these pipelines to look at not just one color or one configuration of gates, but any kind of gate needs to be understood as something to go through, right? So there is domain randomization here. We have the same sensor pipelines essentially. So we have RGB depth segmentation, but we are also adding some new novel sensors like neuromorphic cameras. Neuromorphic cameras are quite interesting because they stream not frames, but they stream events at a very, very high rate, like even up to megahertz worth of updates, which lets you take aggressive and fast actions and so on. So all of these are in the works, and then AirSim Drone Racing Lab is in active development. And yeah, we hope that this would be of good use to researchers. And actually at the end of this webinar, I'm going to use an initial version of AirSim Drone Racing Lab for a quick demo of the features. So here are some links as to where AirSim can be found and all the documentation for AirSim, and also AirSim Drone Racing Lab. As I mentioned, the work that was done with VAE and imitation learning for drone navigation, it's open sourced under Microsoft, so please go take a look at that. And then if you need more information on the Game of Drones competition, there's a website for that as well. And now I'm going to move to a quick demo of the AirSim features. Okay, so in the demo part of things, on the top left, you actually have a view of AirSim. And this is the AirSim Drone Racing Lab, so you can actually see sort of like a racetrack of gates, right? So there's a circular racetrack here. And in AirSim, if you press F1, you get a list of all the options you can play with. For example, there are different camera views we can go over, and different camera windows that we can use for sensor visualizations. So on the bottom here, there's 3 windows, sub-windows. On the left, we have a depth view, And on the middle, we have a segmentation. So you can see all the objects have a specific segmentation mask, right? And on the right, you have the typical RGB sort of a visualization from on board the drone. So the drone has all these cameras on board in a simulated fashion. So let's try to, maybe do something simple. So what I'm going to do first is I'm going to initialize what's called a multi-rotor client. So this gives us access to all the drone specific functions, right? So I'm going to do that. And then I'm going to request to have control of the drone from the Python side of things. So this is all happening in Python right now. So now that I have access by running enable API control, I'm going to try to do the simplest operation, which is takeoff. And the reason I say async is because it's an asynchronous operation that gives me control back once I run the command. As you can see, the drone is taking off. It's flying up to a specified altitude. And then now we can send some arbitrary control commands. So for instance, let's say I want to move forwards with a velocity of 5 meters per second for 5 seconds. So I'm going to say move by velocity, async again. I'm going to say 5 meters per second in the x, and x is forward in this coordinate frame, and 0 on the other two axes. And I'm going to do it for 5 seconds. So the duration is the last parameter. So, and then you can see the drone flying forwards for about 5 seconds. So this is a medium level control, right? So this is velocity control, which is, not the lowest level. We can also move to, for example, certain positions in the world. So for example, I want to go to some arbitrary position, 10, 10, minus 10, and then I want to use a velocity of 2 meters per second. And the reason it's minus 10 is because it's an NED coordinate frame, so upwards is negative. So now it goes to a pre-specified position. So anyway, this gives you an idea of basically some of the common control commands that we can use. And you can think of all of these as actions essentially, right? So if you're training a policy to do reinforcement learning or something, maybe your actions are discrete, right? So you can say move left, move right, move forward. Those are 3 actions. So you can have a velocity command of -1, +1, or something like that for your different actions. So let's go down to like something more reasonable here. Okay, so let's take a look at some of the image pipelines, right? So for instance, in one of the projects I mentioned before, there was this drone detection project, right? And in that project, what we have is we are trying to generate ground truth for detecting an object of interest, which in that case was a drone, right? And in the drone racing lab, maybe we want to detect gates, for instance. So what I'm going to do is I want to generate ground truth segmentation for these gates. So for example, if I have a gate that I need to observe, I want the segmentation map to only point out the gate so I can use that as my ground truth. So what I'm going to do now is let's take a look at the middle sub-window, which is segmentation. And I am going to set segmentation. So I'm going to set all the objects in the scene to the same segmentation ID. So let's see how that looks. I'm going to explain what this command does. Okay, so what's happening here is that I'm taking all the objects in the scene, which is just using a wildcard set of a character, and then I'm setting that to a specific value, and this ranges from 0 to 255 for various colors. So I'm just picking a random color, and all of the objects in the scene are now basically the same color, right? So there's nothing there. But now, what I want to do is I want to focus on, for example, a specific object of interest, which is a gate. So the first thing I'm going to do is I'm going to use the command sim list scene objects. That gives me the list of all the objects in the scene. So these are all the objects that are present. If you scroll up and down, you can see many, many things. So you can have, all the signposts. There is a volleyball net. I'm not sure exactly where it is, but it's somewhere. But here we see the drone gates. Right? So we have gate 0, gate 1, gate 2, gate 3, gate 4, so on and so forth. Let's pick a random gate. Let's pick, gate 7. So let's try that. I'm going to use a function that's called simGet object pose. So what this does is for an object of interest that I'm going to name by the string, it's going to give me the pose of that in the real world. So I'm going to say gate 06. So now we have a pose, which is a combination of orientation and the position. So we know exactly where this particular gate is sitting. So what I'm going to do now is let's try moving that object. Let's read the object's pose again. Sim get object pose 06. And what I'm going to do now is I'm going to try to change the position's x value slightly. So let's, add 10 to it. And then now I've changed it slightly, and I have to command that into the simulation. So now I'm going to use the corresponding sim set object pose. I'm gonna refer to the same gate again, and then I'm gonna say, okay, move to this place. So if you keep an eye on the simulation, you'll see the drone gate has moved by a certain amount, right? So, and then I can sort of repeat that to just move the gate back and forth. So if I decrease it, I can use the same command to bring it back in again. So now that I've kind of made all this objects the same in a segmentation map, let's focus on that particular gate, and then let's see if we can just get the ground truth for that in the pixel space, right? So previously I used this command called set segmentation object ID, right? So now I'm going to get a little bit more specific in here. I'm gonna point to gate 6, and I want to use a different color for that. So I'm gonna just randomly pick 50. So now in the segmentation map here, you've seen that that gate is actually the only one that's showing up. So you can use that as a reference as to compare the RGB inputs to the segmentation inputs, and that acts as your ground truth. And this is essentially what we did for the drone detection project, for the training data. So let's try something else. I can also get the position of the robot at any given time. So I'm going to say simget vehicle pose. So that gives me a pose. So now I'm going to move the drone. Sorry, move the gate 06 to where the drone is currently sitting. So now, okay, so it's essentially blocking the drone, but you can see that it's basically moved over here. So for example, to get training data of the gate, all you would have to do is have the drone at a certain point, and then just keep spawning the gate in front of the drone, in multiple configurations like rotations or something like that, and then you keep capturing data as we go. So this is a very simple kind of an approach that you can do for training data acquisition. And another thing I want to quickly point out is we can also change certain parameters such as the weather in the scene. So for instance, if we press F10 in AirSim, we actually come across a menu that shows us weather options. We can move the sliders around, and then we can have different kinds of weather options. So for example, if I move the snow slider, I'll have a simulation of snow. And of course, the same thing for dust, fog, things like that. So we can change the scene, as much as possible. And you can see all the RGB view is also, replicating exactly what you see in the scene. So when we don't need it, we can just disable the weather by unchecking this box. And it clears up. So these are some simple things you can play with. And of course, there's an extensive list of API on the AirSim website. So feel free to go look at the documentation, look at all the examples that we have. And in terms of drone racing, I just want to focus on one particular example here. So here is an example script, and then let's take a look at this and see how it works with the sim. So in the AirSim Drone Racing Lab repo, we have an example script called baseline racer. And what I'm showing you right now is a slightly modified version of that. So what we are trying to achieve here is one task, which is given a map with a bunch of gates in it, like we've seen before in the game. I want the drone to fly through all of those gates, essentially. So that's pretty much it. So let's take a look at the individual steps that are required to make this happen. So this script actually has a bunch of input arguments that we can pass. So for example, we can pass the level name, which is basically the name of the map, and the AirSim Drone Racing Lab repo has access to multiple of these maps with different tracks. A couple of other interesting ones are you can choose to enable visualization of the trajectory of the drone, and also visualize the image that the drone is capturing through an OpenCV window, and so on and so forth. So in the main function, the first thing that I do is kind of constructing an object that's called baseline racer with a drone name and some of the arguments we've seen before. And I'm going to load the level, which is also straightforward. All of this is being done by like background helper functions, which are not super relevant right now. And then I'm going to initialize the drone. And then if we take a look at the initialize function, this is basically going through the same pipeline that we've seen already. So we are doing enable API control that gives the Python script access to the API of the drone. We make sure it's armed. And then one thing we do here is that we're setting PID gains for the trajectory tracking, actually. So by the function set trajectory tracker gains, the user can choose to have different values of the PID gains, and these will make the drone, as aggressive as possible or as sluggish as possible, depending on what flight characteristics that the user needs. And all the way to the bottom again in the main function, the next thing we do is we take off, and I'm going to explain what the move on spline part is. So if you think about the task that is going through all of these gates, this one assumption I'm making in the script is that I know or I have access to the ground truth poses of the gates. So of course, in real life, if you're trying to build a racing drone, it's very likely you would have to rely on perception to get you those poses. But for the sake of simplicity, I'm just going to assume that we have actual poses. So if we go take a look at this function, that is get ground truth poses, you can see that it's sort of like a mix of what we've seen earlier on the terminal. So the first thing I'm doing is I'm trying to get the names of all the gates in the map by looking at the output of sim list scene objects. So if you remember, we leveraged two functions before for the testing. One of them was sim list scene objects, and the other one was sim get object pose, and then we're going to make use of them again here. So I'm going to look at all the objects that have the word gate in them, so that gives me a list of all the gate names. I'm doing a couple of little cleanup operations here on the strings, and then eventually what I'm doing is for each of those gates in the list of names, I'm going to run sim get object pose, and then that's going to give me the pose of that gate, and I'm going to keep track of all of them by putting them in a little list. So at the end of this function, what I do have is like the ground truth poses of all the gates in a list. So these gate poses, or whatever that we just accessed, they are supposed to act as, intermediate waypoints for the trajectory planner. So the trajectory should be constructed going through these waypoints, and then kind of that will basically become a loop that the drone will follow through all the gates. Before I start flying through the gates, I just want to point out one quick thing I'm doing here as well. This is how we can record imagery from the drone or any other drone state data. So I'm spawning two callbacks here, and then I'm just going to go directly to the main function of the callback. So we have two particular callbacks. One of them is an image callback, and one of them is an odometry callback. In the image callback, I am making use of the AirSim API function called simGetImages. And simGetImages typically requires a request. And here, if you can see line 109, we can see that the request that we are asking for is that of an image type scene. And this is basically the RGB image. We can also change this to depth, segmentation, disparity, depending on what the user wants. So we are requesting a scene image, an RGB image. We are doing a little bit of reshaping operations on that. And finally, if the visualization argument was true, we will go ahead and display this as an OpenCV window. And in the odometry callback, we are making use of another API function that's called getMultirotorState. So this will give us information about the drone's own state at any possible time, right? So we can get access to the positions, the orientation, linear velocity, angular velocity, also the accelerations, but I don't have those lines out here right now. So these two callbacks are basically an example of how you can get other training data, right? So you can record images as the drone is going through its trajectory. You can record its own states to get some understanding of the dynamics or something like that. So I'm going to spawn those callbacks. And finally, the most important function that we have here is called fly through all gates. And let's go take a look at that. So in fly through all gates, I'm calling a function called moveOnSpline async. So moveOnSpline is the backend that we have in AirSim that takes care of both trajectory construction, that's path planning, and also trajectory tracking, which is control. So the main argument for this function is just a list of waypoints that it's supposed to connect. So once I pass like all these gate poses, or the centers of all the gates in the map, the backend in AirSim, what it does, it's basically trying to construct a smooth minimum jerk trajectory that the drone can follow. And then it constructs this trajectory, and then there's a controller that spins up in the background and then makes the drone go through all of the gates. We can also specify like a maximum velocity and maximum acceleration, which are basically being set to some arbitrary values right now, but of course you can play with those values and increase or decrease them as needed. So finally, I'm gonna run this function, and once it's done, because I have a join here to wait for the function to finish, once it's done, I can basically stop the image callbacks and end this whole script. So let's go take a look at how this would work once I run it in the sim. So let's try to run this piece of code. So now you can see that there is a yellow trajectory that's basically showing that the drone is going through all the gates. So of course, all the parameters such as the maximum velocities, maximum accelerations, and even the PID gains, because the drone essentially works using a PID controller. So all of these things can be changed through AirSim API. So we can make the drone as aggressive or as sluggish as we want it. One important thing to note is that the trajectory that's being drawn as a yellow line is actually visible in the images down below. So for actual training data, we want to remove that by passing a parameter that controls the visualization of the trajectory itself. And AirSim Drone Racing Lab comes with these baseline scripts. So you can get started with these spline planners, and any kind of like data recording or data logging kind of features. So yeah, now it's basically completed like full loop, and it's back. It's at the end of the gate. So what we've done now is we tried to come up with a trajectory planning scheme that tries to fit a trajectory through all the gates, and then we asked the drone to go through all of them, and then at the same time we were recording the images and we were recording the data as you saw in the script. So now, because we were talking about drone racing, let's have 2 drones, right? Essentially, that's basically what a race is. So what I'm going to do here is, in the baselines that we have for Drone Racing Lab, we also provide a helper script that is, you can run it as, it's called generate settings file. So this script basically ensures that AirSim knows there are 2 drones. So here we see a sample settings file that was generated by the script I just ran before. So what's happening here is I have a tab called vehicles, and then vehicles contains the configuration for 2 drones now. So you can see drone 1, and on the bottom you see drone 2. So each of these tabs basically has information on, for example, the pose of the robot in the beginning, right? So you can have XYZ, roll, pitch, yaw settings that are the initial positions and orientations. Same thing for drone 2. And for each drone, we can also set specific camera settings. So right now, we're only doing it for drone 1 because that is the only one that's being controlled by the user. And the other one is like an internal AirSim controlled drone. So for this, we can name a camera with some arbitrary name. We're calling it FPV cam. We can set the field of view, which is 90 degrees right now. And we can set the height and the width. Right now, the resolution is 320 by 240, and that can be changed to anything. And all of this data, like the field of view or the orientation of the camera or the position of the camera, they can all be changed through the AirSim API itself. So now that we have the settings file, let's go ahead and try to actually run a race with 2 drones. So here, I am going to run the baseline racer script, which is in the examples, but with a specific flag here. So that is enable viz image CV2. What it does is now it's trying to show me the onboard video of the drone. So I should have access to like an OpenCV window of what the front-facing camera is looking at. So once I run this, so the frame's going to restart. And then again, you can see the objects. Over here, we can see the front-facing camera on the right. And in the game, over the top left, we see a kind of like a race metrics sort of a visualization. So we have access to the race time. We can see metrics like how many gates has the drone passed, and drone 1 and drone 2 separately. So basically what's happening here is that we are using the same technique I described before of like trying to fit a spline and then going through all the gates, but now we are looking at it from a race perspective. So we are trying to fly with respect to the other drone. Right, so looks like we're winning so far. Okay, so this is how you basically can set up an example race and then use it to get some training data. So from this point of view, you can get training data for the perception, like you're seeing on the right from the OpenCV window. You can get data about the actions and the odometry itself, and you can get data with respect to the other drone, right? So maybe if you're losing, you can learn from the other drone's actions to get better and better. So this lets you train your agents for many, many different tasks. So this is kind of like a quick overview of what AirSim Drone Racing Lab tries to do. So it sets you up in this racing environment where you still have access to most of the AirSim API, but slightly enhanced with this concept of autonomous drone racing. So now you can train agents that are not only just doing perception action loops, but they probably are doing it in a competitive fashion. So now you can actually try to beat the other drones, or hopefully beat a human racer in the end. So that was a quick demo of what AirSim Drone Racing Lab can do and how you can sort of get started with, sample autonomous racing drones, right? So these are all the links that might be useful, and you can also find these in the resource list on the platform. And we have links to AirSim Drone Racing Lab itself, and some of the work on the VAE and imitation learning is open sourced, so you can access the code for that and datasets. And also, please check out the Microsoft Game of Drones website, which has a lot of info on how we hosted the previous competition, and hopefully there'll be more to come. So yeah, that's it for this talk. Thank you so much for listening, and I'd be happy to take any more questions in the live Q&A that's going to quickly follow.
Hi, everyone. This is Sai Vemprala. Thanks for attending the Harnessing High-Fidelity Simulations for Robotics seminar. And this is the live Q&A session. And over the next 15 minutes, I'd like to answer some of the top questions submitted by the audience, also some of the questions that we typically get about AirSim and training AI models for robotics in general. So the first question I wanted to tackle, and this is something that we have gotten quite often, is how do we change the parameters of the drone, right? For instance, you might have seen like we have a simple flight, which is a very simple drone platform, right? So if you wanted to, simulate a different kind of drone, or maybe simulate different kinds of physics, for instance, what you can do is it is possible to go into the source code, which is on the GitHub repository. And so one of the parts of the source code is what we call the airlib, which is the main folder, and then airlib contains vehicles and multirotor. And inside the multirotor part of airlib, what we have is a list of parameters that simulate the drone itself. So you have things like the mass of the drone, things like the dimensions, for example, the arm length, other kinds of parameters like the propeller dynamics and stuff like that. So you can always, go ahead and change those inside the source code, and then when you simulate AirSim again, you should see like a different kind of physics simulation. And the other question that I got from the Q&A was, does the camera support distortion models? And yes, this is something that we have on the roadmap as of now. And it's not part of the actual AirSim code, but it will soon be part of the AirSim Drone Racing Lab repository. So please keep an eye on both of those, because the Drone Racing Lab one is under active development, and we are definitely adding a lot of features there. Another question that I saw in the Q&A was, can we directly capture fisheye images using AirSim? And a fisheye image is technically like a special case of a different field of view, right? So it is definitely possible to increase the field of view in the settings itself. So the default is typically 90 degrees, but you can always go over that, maybe like 150, 160 degrees, which is getting closer to fisheye. But if you also want to get like the distorted effect, it goes back to my my previous answer. So this is something that we are trying to implement, and then soon we will have a distortion model, and as well as changing field of view. And one other question I got was, how was the Drone Racing Lab created, and what was the effort that took? So the Drone Racing Lab itself is a collaboration between Microsoft Research, our team, and Stanford University and University of Zurich. So this was something that spun up as an idea for the Game of Drones competition. So as part of the idea of Game of Drones, we wanted to focus solely on the simulation of racing drones, because building a racing drone in hardware is typically hard. So as part of that, we spent a few months, about 3 or 4 months, just coming up with enhancements to AirSim. And so you can see like the V1 of this at the AirSim Drone Racing Lab repo. And then in the future, we want to add a lot more features that are contributing towards robot autonomy. So we are looking at features that will help with mapping of environments and planning and collision avoidance, because that's also a big deal when you're flying really fast. And also at the same time, we are adding other features which will help perception, such as changing distortion models. And we are also looking into the idea of having event-based cameras, for those of you who might have heard about them. So we are looking into many new sensor models and things like that. So please keep an eye on the Drone Racing Lab for more updates in the future. And okay, so another question that I got was, are you able to model energy using AirSim? And this is a great question, because the performance of drones is very, very much tightly coupled with the performance of the battery itself. So this is not something that we have out of the box in AirSim, but there is actually a couple of features that have been contributed by the community. So you may have seen my answer in the audience Q&A. So please feel free to visit the repo, and then if you look for like battery simulation or just battery in the issues and the pull requests, you can actually find some forks of AirSim which have tried to simulate battery capacity and how it changes over a flight. So this is something that is not officially a feature, but it has been added by other people. So you can go ahead and use that, and that's the great thing about open source, right? Because you get contributions from many different community members. And in other question that I have was about how close is this to the typical like the OpenAI GIM kind of a framework. So what we have in AirSim is typically we have access to 2 kinds of clocks. So we have something called a steppable clock, and then we have something called a scalable clock. So the scalable clock is something that lets you simulate faster than real time, or slower, depending on what you wish. And the steppable clock is something that will allow you to sort of pause and continue the simulation. This is something that is getting you closer to like a typical auto kind of paradigm. So although we don't have full parity with the OpenAI Gym framework itself, it is possible for you to utilize these features and then write your own, like, pause and continue sort of an API. And in the future, for AirSim Drone Racing Lab, we would like to actually bring in full parity with like a gym-specific kind of an API. So, it's easier to train our algorithms. And another great question I just received was, how would you tackle learning safety in a drone flying in a simulation? And this is, as I mentioned in the earlier portions of my talk, this is a big focus for us at the Autonomous Systems Group, right? Because safety is paramount. So the way we look at it is, for instance, when I talked about AirSim Drone Racing Lab and I said that, okay, we are going to look at features for mapping and planning. So mapping is typically the one thing that helps you the most with safety, right? Because it tells you where the obstacles are. It tells you what they might look like. And one feature we are trying to add, and which will soon be a part of the Drone Racing Lab, is what we call sign distance field. So this is something that is very widely used in literature. So a sign distance field typically is like an occupancy grid, but with an estimate of how far you are from the closest obstacle. By using features like this, you can learn, really safe operations. So you can know what policy would keep me, as safe as possible given a bunch of obstacles or given other drones flying in the environment. So these are features that we want to add to help with research that is specifically focused on safety. And another question was, other than cars and drones, are there hopes for different modes? So this would be, things like boats or two-wheeled vehicles or different physics models. Again, this is of definite interest to a lot of people because robotics is such a wide array of vehicles. As of now, we are mainly focusing on cars and drones, but because this is open source and because you have access to Unreal Engine, which is a very typical game engine, right? So you do have the luxury to go in and create many different kinds of robots, and also leverage some of the UE physics, which is coming from Unreal Engine. But there is one thing I would also like to note is, apart from cars and drones, we do have a mode that we call the computer vision mode. So what happens in the computer vision mode is that we just take the robot away. So there is only a floating camera, if you think about it. So there is no robot physics. There's just a camera that you can move around. And then, so this is for people who don't really want to deal with dynamics. So if you just want to grab some data from the environment, all you need is like a bunch of images. Feel free to just run it in computer vision mode, and you can see more, more details about this in the repo itself if you look for computer vision. And okay, so another good question that we get pretty often is like, can we run this in a headless mode? And the answer is yes. So the headless mode typically involves off-screen rendering, right? So you're not actually rendering it on the screen because maybe you're running in the Docker image where you don't care about rendering the actual game itself. So if you go in the repo and then you look for the instructions on how to run Docker images, they should give you an answer about how to run this in headless. And another recent question was, is AirSim integrated into ROS? And yes, gladly, the answer is yes. So again, if you go to the repository and you look for ROS, we do have an AirSim ROS wrapper. So this will basically take in all the data that AirSim is publishing in terms of positions, velocities, images, etc., and then just pushes them out as ROS topics. So please go take a look at the functionality there. And if you have any more questions, you can always, for all of you, basically, please feel free to open up issues on the AirSim GitHub itself so we can have more discussion. And yes, another question was, if I want to capture IMU data at a specific location of the drone and have the corresponding images, how do we do that? So this is basically very similar to what we tried in the AirSim Drone Racing Lab demo, right? So we have the move on spline function, and then you can have a callback, which is essentially getting you an image, and then you can sort of, if you have worked with ROS, you would know how the approximate time sync and things like that work. So you could basically have a callback that gets the image, and then right at the same time tries to get the IMU data as well. So we have functions that access the IMU data through, the APIs. There's things like get ground truth kinematics, etc., which are kind of the accelerations and in the gyroscopic velocities and stuff like that. So yes, it is possible to do it. You just have to access the right functions at the callback, and then you can have this callback spinning in the background, right? Another question was, will the second drone always lose? No, it's not. So, so the second drone, if it's your drone, it is definitely possible to understand the dynamics of the first drone, right? And then you should try to, come up with strategies to try to beat it. So this is where it's a really game theoretic kind of a question, and that's why drone racing is exciting. Right? It's not just about perception and planning. It's also about taking advantage and have like adversarial sort of strategies to let you win the game. And is there a way to treat a game window as a video stream instead of collecting single images through image requests? This is a great question because it gives you a higher frequency of data. And yes, the answer is yes. All you would have to do is you can switch to a first-person view for the drone. For example, if you're flying the drone in UE, and like you saw in the demo, you typically have like a third-person view, but if you press F, you can actually go to first-person view, and then it's definitely possible to, use OBS or any of the streaming recording softwares to just record the video. So now you have like a high-frequency video directly from the game. And in terms of this question that I just got about, do you have any chat channel where we can ask questions and get support? Again, the issues tab in the GitHub repository is the best place to get in touch with us. And you can also get help from a lot of the community because it's a very active community on GitHub. It's got about 10,000 stars already. So for people who have already been supporting us, thanks a lot. And then this is a very active community. So please, if you have any questions, feel free to open up an issue or submit any PRs if you have any features you want to see in AirSim. Is there support to run multiple instances of the simulation? So this is a good question. The answer is sort of like yes and no, because yes, you can run multiple instances of the simulation, but what you would have to do is make sure that the API endpoints are all different, right? So you would have to spawn different clients and then also make sure that the servers are all on different ports so you can send commands independently to all of these instances. And one thing to note is also the fact that it's sort of GPU heavy, like AirSim, because of its realism coming from Unreal Engine. It's a little bit intensive on the GPU. So I would, if you're trying to look for multiple instances of the simulation, you would either have to run this on Azure on like a cluster, or you would probably have to use multiple GPUs. And another question was, can we model air or wind? So this is not something that we have out of the box. What we have for wind in the weather effects is only a visual effect. So it just shows you, the weather particles are moving in different directions based on the wind vector. But using Unreal Engine's features, because it's open source and you can just literally download the source code and open it up as a UE game, it is possible to actually have wind vectors that will affect the physics. But this is something that you would have to work on. Another very recent question was, does AirSim use a GPU in headless mode? Yes, because you would still, if you still want to have, first-person camera images and things like that, it would still need the GPU to render them. The only thing that would be gone is like the main game window itself. But there is another version of headless mode, which is like no render, essentially. So we just disable all of the rendering, and you just have the physics simulation. And also documentation for this is, again, on the GitHub repository. Another recent question was, can AirSim tell us about the mechanics and the forces acting on the drone? Also, can the user manually give instructions that is data to train the model? This is not something that we have exposed. So the API that we have exposed are sort of the lowest level you can go to is setting the motor PWMs. So you can just send like motor commands. But if you look at, as I mentioned before in the Q&A, I talked about simple flight and how you can find the parameters for that. So if you go look at that portion of the code and you try to kind of understand how the API generally works, it is possible to expose those parts of the code to the API. So you can probably just send, body forces or body moments like, FX, FY, FZ, or things like that. So that would actually be direct forces on the drone itself, or you can set the forces from the propellers, the rotors themselves. So it is possible to extend the existing API, but we don't have it out of the box. And a couple of other questions that we typically get are basically, different sensor models, right? So people have asked us about thermal cameras or, event-based cameras, like I mentioned before. So we do have, apart from, RGB depth and segmentation, we also have what we call like a mock infrared mode. So this is trying to simulate what a thermal camera would see, but I just want to note that this is not like a fully accurate infrared camera simulation, but this is more of like, similar to segmentation, certain object material types would have certain temperatures, just like an approximate estimate. So there is actually a very interesting project that has used AirSim for detecting wildlife in African forests. So if you go on the AirSim GitHub repo, you can actually find some details about this. And there is also an example environment that sort of puts you in this nice, beautiful African wildlife expanse, and that actually has a simulation of infrared cameras. So that's something you can play with. And cool. And then the question was, what are the sensors that can be integrated, support for RGBD? And RGBD is sort of already there because you do have RGB and you do have depth. And for the depth, we have different kinds of depth as well. So we have perspective depth, planar depth, etc. So it's possible to just, kind of if you're using the ROS interface, for instance, you just pull in images from the RGB topic and then the depth topic, and then that sort of gives you pixel-wise distances for the RGB image. So that should get you close to RGBD. And this is very similar to the kind of work that I kind of talked about for detecting drones through depth maps. So we were assuming that we could pull in RGB and depth. The RGB is useful if you want to run any other perception models. So I guess we have time for one last question. And the question, okay, so they just got this question. How do you build a trajectory when you're not training, but you're testing? Can you touch upon the learning aspect of the drone motion planning? So what you can do is, so with Move on Spline, right, our focus in the talk was with Move on Spline, we were basically trying to learn the velocity commands. But you can actually try to learn the trajectory itself, right? So if you wanted to come up with collision avoidance trajectories, you could have Move on Spline as the ground truth. And you train on Move on Spline, and then you train so you can understand how to fit these trajectories. And then at test time, you basically just spin this up. And based on the environment and based on your location, the obstacle's location, your trajectory planner would be like a learned trajectory model, right? So and then you're just replacing Move on Spline with your own version of it. So in the interest of time, I will have to end here. I'm sorry I'm not able to take most of the other questions, but feel free to open up issues on the GitHub repo, and we can have more discussions over there. And so again, thank you all for attending and then sticking around for the Q&A. We really appreciate your participation and the interest, in this subject. So again, please go take a look at the resource list on the right. This will have links to all the GitHub repositories that I talked about, as well as all the papers that I talked about. And special thanks to all the researchers who have agreed to showcase their research in this talk. And we have links to the AirSim Drone Racing Lab as well as AirSim itself. And then you can look at the repos, you can open up issues, look at the source code, read some of the papers. And then we really look forward to seeing how you use this research and how you build upon it and evolve AI and robotics, because I strongly believe that is the future. Again, thank you very much and have a great day.